It's similar to medical protocol. So what's their so I'm asking the purpose why you know yes. What is that is close to the just that the this numbers to describe the position of the search amount that is a related to celestial coordinates with it. One is for precise measurement and tracking. You cannot track or measure something as long as you cannot put well-defined coordinate systems. And also, if you know the movement of, if you know the orbit and the trajectory of a celestial object, and you establish well-defined coordinate system, you can still predict future events. When hundreds or thousands of years possible. Now, before I cover any coordinate system, I would like to mention the celestial sphere. So, celestial sphere is a apparent sphere of infinite radius, where Earth is at its center, and all the planets, stars, and all the celestial objects are thought to be on the inner surface of this celestial sphere. You can think of it like this. At night sky, you see all the stars and planets. Now, it seems as if all the celestial objects are on the surface of a big sphere. So, this is the celestial sphere. This is not something literal, it is a geometric concept that works as a very powerful conventional tool for our understanding. Now, I'm talking about the celestial sphere. Let's define some important features of this. Let's look at the celestial sphere and Earth that is anyway. So imagine you're just standing here. This is you on the surface of the Earth. Now the point directly forward and upward that intersects the celestial sphere. This one is called the ring. And similarly, the point which is directly under bit of yours, it is the opposite of ring. It is called ring. And when you look up at the sky, you can level to the entire sphere. And at a certain point in time, you can only see a sphere. Because half of the sphere is being blocked by the Earth. Now, the point where the surface of the Earth meets the sky, that is called the horizon. This is the horizon in which and here you can't see below because the surface of the Earth is blocked. Now, let's say this is the equator of the Earth. And if you extend this axis on both sides, you will get celestial north pole and celestial south pole. And unlike Saturn, Neptune, and horizon, this pole is fixed. And Zenith, Neptune, and the horizon is observer dependent, which changes with observer. And now, as I have not situated this time, if you project this light on project this on the celestial scale, you will get what is called the celestial keeper. Now, Vivian is the point that is it's a great circle joining not through your zenith to the south pole. This is called the meridian. And we'll talk about ecliptic later. Now we see the horizontal coordinate system. This is entirely based on the observer's location, this coordinate system. Well, every coordinate system, we need to establish some reference points. In this horizontal coordinate system, our reference point is the orbital horizon. This is also a total one, which means that all the observations taken from the surface of the Earth. In this coordinate system, you need two coordinates to explain the position of any celestial object, that is altitude and azimuth. Let's say you have a star here. Now, altitude is the altitude of a star is the um, angular distance of the celestial object from your horizon. This is called the altitude, and the azimuthal angle is taken from south. Azimuthal angle is basically this angular distance, which is taken from north to east. Now, this altitude can vary from 0 to 90 degrees. If a star's altitude is 0 degrees, it is on your horizon. It will be on your zenith. And this angle, that is the azimuth angle, it varies from 0 to 90 degrees. It is at 0 degrees from north. Now, any celestial object can be defined as this two coordinates, altitude and azimuth. Now, let's look at some examples. A star that is rising from the east, it has very low altitude. We are talking about a star that is just rising from the east. It will have very low altitude. Its azimuth angle will be 90 degrees because it is in east. Similarly, a star setting on west, it will have very low altitude and its azimuthal angle will be 70 degrees. Now, let's say during the motion of a star, let's say a star is the trajectory of the star is like this. It will going from east to west. Now, the moment when it will cross your meridian, this point is called a transit. At transit point, the star that is following this trajectory, it will be closest to the zenith. At that point, you can say that the star is on its highest position in the sky. You see many times that astronomers use this point in time that is called the transit of the celestial object. So study it. Can you just why? Any thoughts? Let's say this is a star. It is on its trajectory from east to west, and during its motion, the moment it crosses the meridian, that is the line joining from north south to your zenith. At that point, the star is at the highest point in the sky because it is closest to the zenith. At that point in time, it is called that moment is called transit, and many astronomers use that moment in time for any sort of measurements for this particular celestial object. So I'm asking any guesses why it happened? Yes, there will be like minimum interference target. Yes, exactly. As you pointed out, at zenith, the star is at the highest point in the sky. So the interference with the atmosphere will be the axis. So it is the prime spot for studying it. Now we have seen this horizontal system, but do you really think we can use it everywhere? Like, what can you tell me the major flaws with this system? It's observability. Uh, yeah. It's observability changes from particular position to another. Yes, exactly. This is both local and time dependent. And see, for as an angle is identified for observer. But let's say you have a friend who is on a different latitude or longitude of star. For them, the stars, the same star's altitude and azimuth angle will be different. So it is completely observer dependent and it is also time dependent. As Earth is rotating, star will shift straight longitude and azimuth angle will continuously change. So we cannot use this system for any sort of catalog. So let's see what we can use first. That's why we define equatorial coordinate system. It is a map which does not move with time. And the fundamental difference from another equatorial system is that in between, like for example, coordinate system, this equatorial coordinate system, the fundamental plane is not the horizon anymore. This is the celestial equator which we talked about earlier. The equator that will allow us to scale. Now, this is our fundamental plane, and all measurements are taken from the center of the Earth. This makes this model geocentric, and at this point, Earth's rotation does not much matter because even if Earth's rotates, its center remains the same. So, if we take measurements from there, it will not change over time. This is the most important of all the coordinate systems that we will discuss today. It's a one more country. Like trivial horizontal system, the reference points there are the celestial equator, that is this red line, and also the Barnell equinox. We will come to Barnell equinox in a moment. I will describe what it is. Let's, let's first see the declination, which is the latitude equivalent of a celestial orbit. Let me try it. Is the angular displacement of the star from the celestial equator. This is represented by Del. And in horizontal coordinate system, this varied from 0 to 90. But here in equatorial system, this varies from minus 90 to plus 90, where if the declination is 0, because the object lies on the celestial equator, and if it is 90 plus 90, is there the object is on the north, and if it is minus 90 degrees, okay. And this is a very important point. We will talk about it later in detail. A star's declination for all purposes we consider it constant. We will see more about this later, but let's just say it is constant. Now, we have defined the latitude equivalent for this system. Now we need a longitude. However, it is not so easy to define a longitude in this system. You see, on Earth, we have taken a reference line that is from north to south to London. That line is the reference, and taking that as a reference, we measure the limits. But here, In this system, Earth is at the center and it constantly rotates. So we can't just fix a point on Earth that will be able to take us the reference. We will see how we will resolve this later, but let me give you a initial solution. That is to define a local equivalent of longitude. We will change over time, but it is extremely useful. It is called the hour angle. It is a time dependent coordinate and local, but so what exactly is the hour angle? Let's say that this red circle is your meridian. Now let's say we have a star here. This angle measured with words is the hour angle, and it is measured in hours. So how can we define it? If the hour angle of a star is zero, this means that the star lies on your meridian. If the hour angle is 5 hours, that means it has already crossed your meridian 5 hours. If it is -1 hour, then the star is on the east and it will reach your meridian in 1 hour, which is equivalent of saying that it has already crossed your meridian 23 hours. Now, this is an important relation. When hour angle is equivalent to 360 degrees. So 1 hour angle is 15 degrees. Now we reach the corner details that I talked couple slides ago, which is the reference point in this equatorial system. So what exactly is this? The great dotted line that you see here is the ecliptic, which is the path that the sun traces in the celestial sphere throughout the year. Now, there are 2 points where the ecliptic will intersect with the our celestial equator. Those 2 points are called equinoxes. During March, around 21st March, we have vernal equinox where the sun, where the ecliptic intersects the celestial equator while moving in the northward direction. That is called the vernal equinox, which is also called the March equinox. We take this point, the vernal equinox, as a reference point to measure longitude along the celestial equator. But before covering right ascension outline from a local sidereal, it's extremely simple. Local sidereal time is basically the hour end of this quarter equinox. Nothing. Now we come at right ascension. Right ascension is the angular displacement along the horizon, along the celestial equator in the eastward direction. This angle is called the right ascension. the star is on meridian, it would mean that the local sidereal time is equivalent to the star's ascension. Right. Now, this is the complete system. You can look at it. Now, this is the conversion formula from equatorial to horizontal coordinate system. You can convert from RF to determinant and vice versa. Where the H is our angle defined by local side areas and minus guidance, and phi is the observer's side area. This is a formula that we don't need to keep in mind because you can just look it up or even not. Now the main question comes: how can we use right assumption and declination to observe stars and other celestial objects? Let's say I want to look at the star series, which has the right assumption coordinate is 6 hours 45 minutes and declination is minus 16 degree length. Now, first we need to find our local sidereal time. Then we can calculate the hour angle using the formula LST minus right assumption. Now let's just say that our local sidereal time is 8 hours. So our hour angle becomes 8 hours minus this, which is 1 hour and 15 minutes. Now what does this mean? It means that the star already has already crossed your meridian 1 hour and 15 minutes ago. Means it is currently on the west. And using declination, you now know the position of serial with respect to your meridian and also know the declination. So you can find it easily. Now we come to this. Okay, let me just ask you a question again. In the beginning, when I was talking about when I defined declination, I explicitly mentioned that for our practical purposes, we will consider it to be fixed and not changing. Now, let me ask you this. Do you really think that the declination will ever change? Any ideas? Often, let me just say, there is a thing called pressing. So, let me define it further. So, this is the this is the Earth's axis, which is dictated by 23 and 180. Now, Earth is not a perfect sphere. It has bulge, which is perpendicular to this to Earth's axis. Now, the gravitational pull due to Sun and the Moon tends to the bulge to make it parallel to the orbital of the Earth's orbital plane. This phenomenon is called the precession, and which is a very slow phenomenon. The axis of the Earth it falls due to this force, due to the sun and moon, the gravitation force. It creates a torque and it woven like this, like a spinning top. So the axis traces out the path during the entire oval. That is this. This is called the precisional cycle. And one entire rotation takes place for it takes 26,000 years to complete one oval. And because of this, the declination keeps changing, even though it is extremely small. Now you may wonder if the declination is constantly changing, how can we define the declination? We need some reference point with respect to which we can define the declination because the axis itself is changing. So we refer to this J2000.0 epoch. That is basically 1st January of the year 2000 at 12 noon. So we this acts as a reference point and the coordinates of all the stars and celestial objects are as if it were on exact time. So even if objects was measured before, it would have been normalized to this. And let's say any celestial object that is discovered after this time, that is also normalized to J2005. Change now. That is the current level and not just this. Now let's talk about ecliptic coordinates. The key difference between uh, equatorial and ecliptic coordinate system is that the fundamental plane or survey, it is not the celestial equator anymore. It is now the ecliptic plane. Let me find one ecliptic latitude, ecliptic longitude. Let's say again we have a star here. Let's say this is the northern equinox. This even this is also a geocentric point, but the center of Earth is the reference. Now, the angular distance of the star or any other celestial object that is above or below the it is called ecliptic latitude, which is represented by and now this angle. Here's also the reference point for measuring longitude in the model equinox. And this angle is represented by alpha. It is the ecliptic longitude. Now you may wonder why even bother with this one? The use cases of this is when when you are measuring any solar system objects, almost everything is extremely close or directly on the ecliptic plane. All the planets, it is almost on the ecliptic plane. So the benefit this gives us is that, let's say you are trying to observe a star, planet on the solar system. Now, if you consider this ecliptic coordinate system, the ecliptic line of the planet will be negligible. So we can completely ignore that and focus only on the ecliptic longitude for any sort of study. And this is also widely used for space missions to other planets because it completely removes one dependency of the coordinate that is we have the ecliptic line and we can do everything with the ecliptic. Now we reach the galactic coordinate system. Here the central reference is the our our reference there is now the galactic plane. You may say, how can we define the galactic plane when we are inside of it? Imagine you're looking at the night sky and you see the entire Milky Way belt. Yeah. So the reference point which is the galactic plane is defined if you trace a great circle along the Milky Way belt. This will give you the galactic plane. And the center of the galaxy which is near Sagittarius Vengeance. This is our another reference point. And the center where from where we will observe, it is considered to be sun. Now this uh, galactic center acts as a reference point to measure the galactic longitude, which is represented by so this you can define the position of usually most of the stars they on the galactic, right? So B is almost zero for most of the stars. Yeah. Well, it's like non-galactic poles like perfect. If they're to be like they are no, it's all perfect. Exactly. Now, it means V to be zero, which is the galactic latitude to be zero. Let's see how if we change the galactic longitude, it will give us different positions of the galaxy. And L equal to zero and zero longitude, we will stare directly at the galactic center, which is the grounded region, and L equal to 90 degrees or 270 degrees particular to the galactic center, and we will find local spiral arcs. And at 180 degree, we will be looking directly behind the galactic, where the galactic center, which is a first common region. Now you might wonder why then use this one. It's quite useful when we are doing study or galactic levels. Like mapping our galaxy, it helps us predict the Milky Way. It can show the overall structure of the galaxy, where the global spiral arms are, where the gas clouds are. It helps us define the structure. Same other galaxy. Here, if you see, if you look directly behind the galactic center, which is around 180 degrees, here you won't find much of a cloud due to the center of the galaxy. So, it is a prize for picture or observe other galaxies or extragalactic celestial objects such as supernova. And also, if you need to observe extragalactic objects, you can okay, so there is a unit observed beyond V equal to 20 degrees. This is the V. As V is low, it will point to the directly to our galaxy. So if you need to observe things beyond our galaxy, your V must be greater than a certain angle. Usually above 20 degrees, we will be very good. Now I have combined this table for the question, which also acts as a summary. If you have fundamental circle, the results point coordinates, the primary state of all of the four coordinates to the R and S right here. You can have a look at it. I will share the slides with you. Now let's talk about diurnal motion. It is not directly related to any coordinate systems, but it is useful to know. Diurnal motion is the apparent westward motion of the celestial sphere due to Earth's eastward. Now, you have seen images like this, which is a very long exposure of stars, and you have seen stars illuminating this a certain height. So basically, what happens is that the stars move across the axis, it is across the north celestial world. Uh, this is the celestial sphere, and this is the north celestial north. The stars tend to rotate from east to west on this axis. And this line, the circular lines that the stars press, is called the diurnal series. So this is a very interesting thing. There are some stars which never seem to set. These are called circumpolar stars that never dip below the horizon. Now, there is a certain rule for a star to be called circumpolar star. The expression is no, this expression is valid only for the number chemistry. For southern, there is a different one. I will talk about it. That recognition of a star was greater than a record 90 minus of the first latitude on the southern hemisphere. So let's just say exactly our local latitude is 20 degree north. So we will get declination of the star has to be greater than or equal to 70 degrees so that it will never set and it will keep circling the celestial body. So if you were in summer as well, the expression is so we left the for five. That is the first latitude. Five probably negative there because in the southern hemisphere it will be. No, I have mentioned about sidereal time. Let's talk about sidereal time. Solar day is measured in reference to sun. The time it takes for the sun to come back to the position it was at noon. Whereas the sidereal day would take the result from star. It is the time taken from the star to come back to the same position. And it is slightly shorter than solar day. It is 4 minutes shorter actually, 23 hours and 56 minutes. And why shorter? It is due to the revolution of Earth technology. Now, we have covered this. Let me tell you about one of the software and databases that you can play around with and look at. Stellarium and Sky Safari. I think every one of you have heard about this. And many of you have already used it. This Stellarium, especially and Sky Safari, they are for real life tracking of celestial objects. You can find the coordinates in any coordinate system using this. Now, the most widely used database for celestial object is Symbol. It is hosted by CDS, which is in France. It has precise measurements and data of millions of celestial objects. And uh, here you will find the coordinates in all of the coordinate systems. All and Astronomical is a Python library where you can with for many purposes with coordinate conversion from Aryan to decimal and many other things. So let me do a quick recap of what we have covered in. We have first talked about the need for a celestial coordinate system. Then I introduced you to the celestial sphere, which is not real sphere, but the imaginary system. It's a good conceptual. We have talked about the horizontal coordinate system and its flaws. I have talked about the equatorial, the hour and coordinate modern equinox, and the local sidereal. I have also shown you the converter formula from RNX to fault alignment. Then I have discussed about epoch and precision, how precision changes declination, and what we use as standard epoch. Then we have the ecliptic system, which is used for mainly for solar system objects that is on or close to the lens. We have then galactic system, where we use for to study structures of the galaxy and planets. Then we have seen diurnal motion, circumpolar stars, and the rules then that allow that defines a circumpolar star and the sidereal versus solar. And then we have also looked at softwares and data. So this concludes today's talk. Thank you very much. So, stop.